a Lenovo. Board number is LA9901P. Alright, so a friend mine said that he wants me to do a video on RAM after the CPU gets the reset signal. What happens after the CPU gets reset signal? Alright, so as you know, this is a soft start process, and CPU will start to search for the BIOS. Right, so the BIOS, after the CPU gets its working condition of supply, we have all supplies like VCC core, VTT 1.5 volt or 1, since this is a DDR3 motherboard, so this is a 1.5 volt supply, so 1.5 volt supply coming, right? So we have our next one, we have DRAM power good, host power good resets, and hosts, and then the PLT reset signal. Once those working conditions is okay and the CPU gets all its working conditions, then it will come through the DMI bus. Now the DMI bus will come through the PCH, and then the PCH will what? Read the BIOS immediately. So after checking all supplies and all working conditions is okay, the PCH working condition is okay and it's in order, then it will come through the PCH through the DMI bus through the SPI bus to read its BIOS, as you can see. Right, so once its BIOS is okay and intact, and it will then send a reverse instruction back through the DMI bus to the CPU that the BIOS is okay, and then now it will start to run the code, and then it will come into RAM. So to confirm this, there are two pins on the RAM that we need to check, which is SMB data and SMB clock. Those two signals you have to check to see if the RAM has passed. If there's no waveform on those pins, then the CPU doesn't run code, no display. Right? There's no code. What code means is that there's a code inside of the CPU, an address inside of the CPU and inside of the BIOS chip to find that addressing instruction so that it can run the code. That is why when you use the debug card, this is where the debug card comes in to run the code. If there's no code, no display. If there's a fault with the DMI bus, no display, and the RAM won't initialize, because you need to initialize the RAM in order to run the code. Right, so this is where the CPU and the memory comes in, and the CPU comes in action. Alright, so this is based on soft start, a slight soft start. So I will focus my entire focus on this part. So as I said, assuming that the CPU gets its reset signal, then we are going to check if the BIOS is being read. So we are going to use our oscilloscope here, and as you can see, this is a Regal DS1104 oscilloscope, which is a 100 megahertz oscilloscope, 4 channel, right? And this is we're going to use one channel 1, as you can see, and we're going to check each step of the way to see if the CPU has passed and the CPU has run the code in the RAM, and the RAM is being initialized, right? And everything is initialized. The graphics card, this is a discrete motherboard, as you can see, all right? And this one uses a NVIDIA, right? NVIDIA NM14 GE, and this is a NM14. This is the 4th generation of the NVIDIA graphics card, right? A VRAM of up to 512. It can support up to 2 gigabytes of VRAM, right? NM4, you have NMP DDR3 8, and you have DDR3. So these are two versions. So you have NM14P and NM14M, right? Which is supported DDR3 up to 4, right? And DDR3 8, right? So this is the total of the of VRAM that can be supported. So you have 512, 1 gigabyte, and 2 gigabyte. But the focus is on RAM. After the CPU gets its reset signal, host reset signal, how to check and how to confirm if the RAM and the CPU has passed, right? And the code has been run, right? So let's start. All right, so I will use oscilloscope mostly. As you can see, I'll maybe use the multimeter just for voltage testing purpose. This is a fluke. All right, so this one is a RAM coil. This one is a RAM coil. So this is the back end, and this is the front end. All right, so let's turn on the board. Remember, CPU gets RAM, so all supply is okay. All right, so the board is on. Measure. As you can see, this is 1.5 volt. This is RAM supply, right? And this is pouring the RAM and the VDDQ RAM section inside of the CPU, right? So this is another this voltage is going to the RAM slots, and it's also going to the VDDQ module inside of the CPU, right? Very important. So once the CPU working condition is okay, then the BIOS is gonna be read. All right, so we're going to check if the CPU is reading the BIOS. Let's see if the BIOS is being read. Next, we are going to check. I'll plug it out. Oh, I see. All right, so we're going to check the chip select signal. Remember, the BIOS chip has a chip select signal here to know, so we can use as a measuring point to check with our oscilloscope. So this is the scope, channel 1. We'll just use channel 1. All right, channel 1. All right, so this is our oscilloscope, as you can see. All right, and this is the run stop, means it's on auto. Sorry. Both says an auto. All right, so this is a 4-channel 1, 2, 3, 4-channel oscilloscope, right? And we're going to check the BIOS with the channel 1, right? And then we're going to set up the trigger settings. Very important. So the first thing when you're setting your trigger settings, your type must set to edge, right? Our source is channel 1 because we're using 1 probe. Our slope, because we're measuring a falling edge. Remember, when the BIOS is being read, it goes from high to chop the 3 volts, so you need a falling edge, not a rising edge, because the BIOS basically reads chip select and the signal falls, so it chops the signal, the 3 volt into several pieces then, right? So we need to set this to falling edge. No, this slope is set to rising edge, so we need to set it to falling edge, which is this one. All right, this is falling edge. All right, select that, and this is a falling edge. See the arrow, falling edge. Now let's go to the single trigger, because the only way we can catch, you can set the oscilloscope on the auto to catch the BIOS signal chip select, but it's preferred to use it on a single trigger so you can analyze the waveform. All right, so I'm going to do it in both ways, in normal auto and in single trigger. So let's go on auto. All right, and make sure that my position here is set to our volts per division to about 1 volt, right? So each division is 1 volt, so this is 1, 2, 3, 4 volts, right? So each division is 1 volt. This is your voltage, this is your time base, right? So this is your time, and it's located up here as 50 milliseconds, right? And we're going to set up, this is on auto. All right, so I'm going to set my BIOS probe. This is pin number 1. This is chip select, so this is pin number 1, 2, 3, 4, 5, 6, 7, 8. This is the supply, this is chip select pin number 1. So I'm going to make sure my horizontal position here is set to 0 volts. 1 volt per division. And we're going to turn on the board. Let's see, watch the screen as I press the power button. This is chip select. See? BIOS is being read, and then it goes away. So that's a perfect way we can know that the BIOS has been read. Alright, so let's set this back to 0 volts. Right? And we'll set this back to 1 volt. Alright, so let's go again. As you can see, the BIOS, the CPU, the CPU is reading the BIOS through the DMI bus. As you can take a look, I hit the power button. See, the BIOS has been read, and then it stops. So that's a perfect way for. We're going to look at the single trigger now. On the trigger, we're going to do the same thing. Now I'm going to set up my control, which is 1 volt per division. The slope is set to falling edge, right? And my trigger level set to single. I can now set my trigger level up to about 1.5 volts. All right, my single trigger set to 1.5 volt there. Now, as I set it back to single, now I'm going to connect the adapter. Alright, so as you can see, we have the wait option here, and this indicates that we're in single trigger mode and it's waiting for a trigger and it's listening for a signal. right? So I have my voltage per division set to 1 volt per division. Also it's set to single trigger mode. As you can see, the trigger, right? I can hit mode and I can disable. I set it to auto sweep, single, right? And it's on waiting. So I'm going to hit the power button now. Good. So as you can see, our BIOS has been read, and as my control set to 1 volt per division, right? 1, 2, 3, 3 point up to 3 volt, 3.4 volt, right? And my trigger level is set to 1 volt. And let's take a look at this waveform, right? So as you can see, the BIOS has been read perfectly, and this is reading in sequence. Because of the model of this oscilloscope, the BIOS read is a bit different, but this is perfectly fine, as you can see. So the BIOS has been read, and the CPU is okay. So that confirms that the DMI bus is okay, right? The DMI bus in the CPU and the PCH is okay. So the next thing now, we want to know that now the BIOS is being read perfectly, as you can see, right? And we can save this for reference, right? So we can save this. So to do that, we have to insert the jump drive. You click storage, right? Once you click storage, then the picture you want to save it as a ping, and then you select save, right? You want it as a JPEG file. We have bitmap, JPEG, TIFF, and the different file formats for the images that you want. So normally we use JPEG, right? And it's actually an image, and then we can click save, and then you select the source, local disk, or you can save it to a jump drive if you want, right? So the next signal we're going to check for now is the RAM. So let's remove the RAM. So on a DDR3 RAM, there are 2 pins, pin 200 and pin 202 on the DDR3. So to confirm, let's go to the schematic. Alright, so this is the memory slot and the schematic, and as you can see, we have here various pins. So we have like the voltage ref, very important. This is one of the working conditions. We also have VDDQ, which is the primary voltage of 1.5 volt. Then we have clock, enable clock 1, and we have DRAM reset, pin number 30. Very important pin. DRAM reset is a very important and crucial. This signal is, that means everything is okay with the PCH, right? Reading the RAM, right? And then once that is okay, the RAM will be initialized. So once the RAM is being read, right, the power supply is okay, which is 1.5 volts. We have VTT, which is the termination supply. How much voltage is that? The termination supply is half of the reference voltage, which is 1.5. That's 0.75 volts, right? So that's 0.75 volts, which is the VTT supply, right? So let's find it. Oh, it's over on the next side, I believe. Oh, it's everything's crammed on one slot. So that is VTT. So let's look for VTT. On some schematic, they will organize the signal, and so it's easier. All right, so we are gonna look for on that termination. So we'll get to the pin 120, VTT. See, VTT 0.75 volt, which is half of the VDDQ, which is the reference voltage. This is the primary. See, this is the working conditions. This schematic gives us all the working conditions. See, first you check 1.5 volt is coming, then second you check VTT 0.75 volt, then you check the reference voltage. Now the reference voltage is equal to 1 times, which is 1 times a 0.1 microfarad and a 0.1 to the 2.2 microfarad. VDD SPD, this is the RAM, this is the Eprom chip supply from the RAM. So this RAM has a small Eprom chip, as you can see, and that is the supply, which is 3.3 volts. It's point pin number 8 on this RAM chip, and that goes directly to this, right? So these are the working conditions. Some of them, as you can see, this is the voltage reference. Yeah, voltage reference input and voltage reference output. We have ODT on the termination, but these are not necessary right now. We are just focusing on the code, what happens after the CPU gets its code reset signal, right? So I want to get this full information, I have to pay, so I can't give all this information. All right, so the next signal we're going to check is pin 200 and pin 204 SMBUS clock, pin 200, SMB data pin 204, SMB bus clock. So let's go down, see? 200 and 202 and 200. See? SMB data, SMB clock. These two signals, we should check to see if the BIOS is being read and it is passed into RAM. So let's set up our trigger level. So first, we need to clear that. We're doing it without RAM. So this is the memory slot, and alright, so this is the memory slot. So this is pin 203, right? Pin 203, pin 204. So this will be pin 200, right? See, 203. So this will be 203 here, 204, right? 203, 204, 201, 202. So this is pin 202. We're gonna check these 202, right? And this is pin 200. So if we turn them on, if these should give us 3 volts, which is pulled up all the time. So let's measure that. So let's turn on. So pin 200 and 3.3 volts. 3.3 volts is there. Pin 200, 3.3 volts. So this is the clock and data signals, right? Right, clock and data, 300, 200 and 202. So we're going to check those two signals with oscilloscope. So first we have to go back to the oscilloscope. We have to set up we have to change all the settings inside of our oscilloscope. So let's set up that control. So first we should have our voltage to 1 volt per division. And second, we have to set our voltage to about our voltage set to 1 volt per division. Our time base should be set to microseconds. So you should see US. This is nano. So let's go until we find US, which is microseconds. So we set this to about 100 US. Our trigger level should set to 1.5 volts since our voltage range is 1.5 volt. So let's go up to 1.5 volt. We're going to check RAM, VDD, RAM, SMBUS and SMB clock and data signal, which is an I2C, which are known as the I2C bus, right? Any SMBUS is I2C bus compliant, right? So let's check. So I have already set up my oscilloscope at 1 volts per division, right? My time base is set to 100 microseconds. It can go up to 200, between 100 to 250 microseconds. So we're going to check, right? So let's clear that. Single trigger, and I'm single, right? Good. So our trigger menu is here, and we are going on the falling edge. Our source is set to channel 1. Our trigger is set to edge, and we are on the single sweep, right? Very important that you set this. If your oscilloscope is not set on this, it's set on the rising. This is, sorry, let's go up. This is not the right way. This is when you're checking an inductance back-end waveform, right? So if you want a nice rising edge like from here and a nice slope, then you set it to this, just like when you're going to check the RAM. For example, let's check the RAM supply. This is the RAM supply. This is the inductance back end, right? So let's turn on the board. No, oh, that's the front end. Let me clear that. My mistake. This is the back end. So we should get a straight line coming from like this. So when you're checking the oscilloscope, on any back end, you should get something like this. Right? Right, that's a rising edge. This is a falling edge. Right? So this is the right, this is how, when you're checking BIOS signals, RAM signals, high frequency signals that has a lot of pulses, you use a falling edge. Right? Because there's a lot of pulses. If you're checking a voltage, you use the rising edge. Right? So the slope depends how sharp, right? How the slope rises. So that determines, as you can see. Right? So let's, now I've got it. So as you can see, this is the data. So this indicates that the RAM has been passed, and you can see that this is data, That's pin 200. This was pin 200. And that's data. Good. So this is a perfect waveform, right? And that's the RAM has passed. Right. Next, we're going to check the clock. So this two signal I should check to know if the RAM has passed or not. Right. And this is clock. And we're going to check the next one. Alright, next we're going to check clock. Let's check clock. That's pin 202. Alright, so pin 202. Pin 202. Now we're going to check the clock. Good. So as you can see, this is clock. Now if we save these two waveforms, you can see that the two waveforms are different. So as you can see, right, my voltage is set to 2 volts per division. So let's move this up. So this is 2 to 2. This is 2 volts. Right, if I set this to 1, for example. So this is 1, 2, 3, 3.3 volts, right? So this is 0. Let's put this on a 0 position, all the way to 0 on the 0 line here. Perfect, perfect. So each volts per division. So this is 1, 2, 3 volts, eh? So that's 1 pole per division. This is the clock. So you see the difference between the waveforms? These are the two different waveforms, and this is a perfect action of RAM. So the code has been passed. So after the CPU gets its reset signal, you should check pin number 202 and pin number 204, and this is how you can get and know that the RAM is working, right? So this is a perfect waveform, and this is our time base, right, as you can see, and this is RAM in action, right, and this is a perfect. All right, so pin number 30, as you can see, is very important, the reset signal. This is the next signal you should check. Once checking this signal, everything is okay. The RAM has been passed, so clock data is passed, and then the RAM reset is okay. Then this is 1.5 volt coming to pin number 30. Yes, coming to pin number 30 on the DIMM slot. This is pin number 30, DRAM reset. Right, and this is pin number 30. So without RAM, this voltage will not come. So on oscilloscope, we'll get only a rising edge like this. Right, on oscilloscope, this will be DRAM reset. And that's not a valid reset. This is a valid reset signal. Right, that's DRAM reset, 1.5 volt hash. Pull down low, active low. Right, so on the oscilloscope, you should get a waveform like this. Right, if there's no RAM, you get this waveform. So let's check. All right, so probe. First, let's turn on the board and let's check if the 1.5 volt is coming or not. All right, let's turn it on. 1.5 volts is there, so this is the RAM reset. But as I said before, you get a rising edge. So once the RAM is in, you will get a falling a waveform like that. You'll get the waveform like this. So let's oscilloscope, single. All right. See that? This is reset. See? You see that? You see that? That's a complete reset. So the waveform is just like this one, as I showed you. Right? See? So this is the reset signal. So once you get this signal, what does that mean? Anybody can tell me?
System perfect.
Everything is okay.